And now for the introduction of today's speakers. Our first speaker is Autumn Phillips. Autumn is a technical support chemist at Inorganic Ventures with experience in bulk scale manufacturing, reaction and purification performance, and improvement. She has extensive background in manufacturing custom CRM products. Autumn received a BS in biochemistry and a BA in chemistry from Virginia Tech. Go Hokies. Our second speaker is Dr. Paul Gaines. Dr. Gaines has nearly 4 decades of spectroscopic experience. After earning his PhD in chemistry at Iowa State University, Paul worked in the laboratories of Exxon Research and Engineering and also Union Carbide. Today, Paul is the Senior Technical Advisor and Chairman of the Board of Directors at Inorganic Ventures, as well as an accomplished web author of many popular guides and papers for fellow spectroscopists. So now, without further delay, I will pass it off to Autumn.
All right, thanks, Thomas. And thank you everyone for joining us this morning. As Thomas said, my name is Autumn Phillips. I am the technical support chemist here at IV. And today, Paul and I are just going to be discussing some of the main issues we see with analyzing tin and mercury via ICP. So we're going to start off with mercury. We're going to go through a little bit about the different forms of mercury in solution and how to keep it in the correct form. Then we're going to go through some sample prep for different types of samples. And then we're going to go through particularly ICP issues. And then we're going to do the same thing for tin. So mercury is definitely one of those problem elements. Chances are if you've worked with mercury or analyzing mercury in the lab, you've run into issues at some point or another. But it is very important to still determine mercury content. It's got many different applications in environmental testing, pharmaceutical, dental, lots of different applications. So it's important to know how much mercury is in your sample for safety reasons, primarily. So the majority of the questions that we receive here at IV relating to mercury relate to ICP analysis specifically. And so kind of the main point that we want to focus on for mercury is that it needs to be in the mercury +2 ionic form to get accurate results on your ICP. So that's going to bring us to our first polling question. We kind of just wanted to get a little bit more information about our audience and what industries you're from. So I'm going to give you a few seconds to go ahead and answer that. Give you a couple more seconds here. All right, so it looks like the majority are environmental related. So that's good to note. We just wanted to see kind of who our audience was, not only for today's talk, but for future talks, so we can make sure that we're giving the most relevant information for you all that's going to be helpful. All right. So how do we keep mercury in that +2 form? Well, the first thing you want to avoid is using neutral or basic media. You want to keep the pH acidic, because if not, you can form that insoluble carbonate. Another thing you want to avoid is tartrate. Tartrate can reduce the mercury to the metallic form, which will result in loss of your mercury, as that is a volatile form. So we use tartaric acid to stabilize our antimony standards, some of our antimony standards. So whenever we're mixing antimony and mercury, we have to make sure that we're using the antimony stabilized in HF to avoid those issues with mercury and the tartrate. So another thing you want to avoid is reducing environments. The mercury 2+ form is pretty easily reduced to the diatomic mercury, or the dimer, which then can disproportionate into the metallic mercury and the ion. So again, you're going to have loss of mercury there if that disproportionation does occur. Another thing you want to keep in mind is if you have leftover NO2 gases from your production reaction process. You want to make sure that you're heating to expel all of those so that they're not remaining in the container, as those can also reduce the mercury ions to the diatomic mercury. So this can be fixed if you boil the standard with excess nitric acid. This will convert the diatomic mercury back to the ionic form, the mercury 2 plus ionic form. But again, recertification may be required in this case because you are adding, additional volume and then boiling down. So you want to make sure that if you do use this process, that you still know the concentration of mercury in your standards. So now I'm going to turn it over to Paul to talk a little bit more about the chemistry of mercury with these NO2 fumes and kind of how we figured out that this was occurring early on in our standards.
Thank you, Autumn. This slide really shows the the elemental mercury with the metallic mercury, we dissolve that with nitric acid, with a high purity nitric acid. This reaction gives off a lot of brown fumes, which you get when you dissolve metals with nitric at relatively high nitric concentrations. And we will heat to get rid of the NOx fumes, but it's the NO2. That's the path that nitric acid takes for a 1 electron reduction. It gets reduced, the mercury gets oxidized to the +2. We dilute the water and then we make our stock products and concentrates. And we have 3 different ways of checking the mercury content. One is with an EDTA titration. Now that titration reacts only with mercury in the +2 state. Another one is ICP assay, which will detect any mercury that's in there. But if it's in there as free elemental mercury, it'll give a false high result because of a higher nebulization efficiency, the vapor pressure of the mercury. And then we do just the elemental weighing it out as a gravimetric is the third way that we check. Now, we know that our mercury is good if we get our EDTA and ICP results to agree. If there's a little bit of elemental mercury in the blend, the EDTA results will be low. Now, the chemistry that really is causing all the trouble is this disproportionation reaction shown on the bottom of the page where the diatomic mercury gets reduced to elemental and mercury +2. In reality, there's no such thing as a mercurous mercury. You hear a lot about it, but the Hg2+2 is actually an Hg2+ and an elemental mercury because it is not paramagnetic, it's diamagnetic in its behavior. No, there's no unshared electron. So what we're dealing with are situations where your mercury in your sample or in your standard bottle is getting reduced and then forming the diatom. The equilibrium is such that it's about 1,000 times more wanting to form the diatomic mercury than to be the free mercury. So you've got a thermodynamic equilibrium that is going in that direction. But when you add ligands to your mercury, if it has any diatom, it will break it into the Hg0 and the Hg+2, the mercuric and the elemental mercury. So the problems that you're having, one of the ways it manifests itself is if you make up a set of standards and you take a reading and the numbers come out, they seem to be a little high, but then you take them again and again, you go the next day and it's stabilized, everything looks stable. And some people refer to it as aging their mercury standard. It's not a good sign. If you're getting results that are changing, it tells me that you've got some of this going on, that you've got some elemental mercury that's in there. And as Autumn just said a bit ago, the way to get rid of that is to take your mercury aliquot and heat it with nitric acid to make sure something hasn't gotten in it, a dirty pipette tip or something with enough reducing agent to bring the mercury to the mercurous, listen to me, to the diatom. I still do it. We used to think years ago it was mercury in the +1 oxidation state. Thank you, Autumn. I think that's all I've got for this one.
All right, great. Thanks, Paul. So what type of matrix do we want to use for mercury? Well, a lot of analysts like to use nitric acid for their matrices because, it's not going to have interference issues in your ICP. But there are issues for using nitric acid alone for stabilizing mercury. So in nitric alone, mercury will adsorb to the walls of plastic containers. So this is really going to be mainly a concern for low-level mercury standards. We generally don't recommend using plastic containers for mercury standards in nitric alone at 200 ppm or lower. So an alternative you can use is borosilicate glass containers. But again, there are going to be concerns for glass because glass is going to have higher levels of contaminants. We've done leaching studies and found that the elements listed at the bottom of the screen here are going to be the contamination issues you're going to want to look at. So if these analytes are in your samples or standards, glass may not be an option depending on how low of a concentration you're looking at. Another issue with using glass containers is if you have HF in your standards, these are not going to be compatible with glass because the HF is going to be caustic to the glass. So you're going to leach out all those impurities that you don't want and also potentially compromise the integrity of the container as well. So just some things to consider if you do want to use mercury and nitric in glass containers. So another option for stabilizing mercury and nitric is adding 1 ppm gold trichloride. The EPA released a bulletin detailing this recommendation, which can be found at the link in the first bullet. So this is going to prevent the mercury from adsorbing to the surfaces of your plastic container. And we have used this process here at IV, and it's worked very well for stabilizing lower level mercury and nitric. But one thing you do want to consider is if you are analyzing via ICP-MS, there is going to be that polyatomic interference for arsenic and selenium. So if you have arsenic or selenium in your analysis, you do want to account for that. So because the chloride level is going to be so low from that 1 ppm gold trichloride, you can just make sure to add the same amount of gold trichloride to the matrix of your blanks, standards, and samples, and that should account for any interference issues that you would have. There's also another method that we've heard of using L-cysteine to stabilize your mercury. We have not used that method in-house, but if you are interested in learning more about that, we've linked a paper by Steve Pappas at the bottom of this slide if you do want to see how that's been used. And we have heard that analysts are getting good results with stabilizing their mercury with the L-cysteine. So the next matrix option is hydrochloric acid. We generally recommend using hydrochloric acid as the matrix if possible for your mercury standards. Mercury is going to be stable in both glass and plastic, so you don't have to worry about your container material. But again, you do have that polyatomic interference from the chloride for arsenic and selenium. But we just mitigate this issue by using the collision cell or ICP-MS, and that's going to eliminate any of those interference issues if you do have arsenic and selenium or selenium in your analysis. So another concern is for that disproportionation of the diatomic mercury from interaction with the chloride into the metallic mercury and the mercury +2. So one way that you can make sure that there is no dimer in your standards is to go ahead and weigh out your aliquot so that you know you've already measured out the proper volume of the standard that you want to add, and actually boiling the aliquot with nitric acid to make sure that you don't have any of that dimer present. Another consideration for using chloride is if you have silver in the analysis, silver will precipitate with trace chloride. So you want to make sure to overwhelm that with an excess of chloride to keep your silver in solution. And so if that is a concern for you, you can just reach out to us and we can give recommendations for how much chloride is going to be needed based on your silver concentration. And those standards, if you do have silver and HCl, they will be photosensitive, so you're going to want to keep those away from light as much as possible. Another analyte of concern is thallium. So thallium in the +1 oxidation state can precipitate with chloride. So if you do have thallium in your standard, you're going to want to make sure it's in the +3 oxidation state. One thing to note is that our stock standards for thallium here at IV are all in the +1 oxidation state. So if you are using chloride for the analysis, make sure that you specify that when requesting the quote, and we can provide custom standards with this thallium 3+ to make sure you're not going to have any issues for loss of thallium with HCl. So that brings us to our sample preparation. For mercury digestions, we always recommend using a closed vessel to make sure that you're not losing that mercury and also that you're not releasing the mercury into the air for safety and toxicity concerns. So along with that, we do recommend avoiding ashing just due to loss of your mercury. It's just not going to probably be the best option for the digestion. So for the metals or the oxide, it's probably just going to be easiest to dissolve in nitric acid. That's how we prepare our mercury standards here. It's a really easy, simple digestion, so no issues there. However, for organic mercury compounds, things do get a little bit more complicated. So we're going to talk about that in the next slide. So I just want to start off by saying that any organic mercury compounds are going to be extremely toxic. That's one of the reasons that we don't work with organomercury compounds here, is just for the safety concerns. So if you are working with these, just make sure that you're using extreme caution and operating under proper safety measures. So mercury needs to be kept in solution with an oxidizing agent. Otherwise, it will be reduced to the metallic form and lost from your sample. So generally for biological material, we recommend heating your sample with either sulfuric acid alone or a combination of sulfuric acid and nitric acid, along with an excess of potassium permanganate. So the permanganate is going to act as the oxidizing agent to keep your mercury in solution. And the reason we recommend adding nitric to this is because sulfuric alone may not fully free all of your mercury. So you want to add a little bit of nitric if you can to make sure that you've gotten all the mercury from your sample. Again, for these type of reactions, we do recommend a closed vessel and low heat. So you're not going to want to take this over about 50 to 60 degrees Celsius, but it should work well under those conditions. Another option instead of permanganate is you can use perchloric acid as the oxidizing agent. And so I'm going to turn it over to Paul to talk a little bit more about the use of perchloric acid for these type of reactions.
Perchloric acid digestions are ones that I've had the privilege of using, the opportunity to use now for, gosh, a long time. And at Iowa State University, perchloric acid was kind of like the main acid. That's really kind of where it started with G. Frederick Smith and the work that he did back in those days. Perchloric acid is an extraordinary molecule, extraordinary chemistry. It can be very safe if you know how to use it. Our trace analysis guide, section 12, goes into safety aspects of that. And without going, but if you get on our website, go to our trace analysis guide, please, in section 12, and that will take you to a discussion of oxidation of organics. It'll talk about perchloric acid and will highlight the safety features. And the guide is written very direct and very straightforward. There's not a lot of reading. It's mostly information is, a lot of information is given in a small amount of space. But information that is very, very useful and very key. When you're doing an oxidation such as this, you've got to be aware of the fact that there are two classes of compounds that can be very hazardous. One are your alcohols, your organic alkyl alcohols. That will react with nitric acid to form, literally can form a flame, a fire. I've seen the fronts of ICPs engulfed in flames when alcohol solvent, such as isopropanol or ethanol, is mixed with enough nitric acid. The explosion hazard is one too, where you can form nitroglycerin. Another compound or functionality we want to be careful about is the aromaticity. You can form compounds, nitrate them, and form things like TNT. So my general rule of thumb is I recommend, if you have access to an infrared spectrometer, do an infrared scan of your sample before you try, or sample types to try to digest. If you're going to use this kind of digestion, make sure your functionality is safe. If you think there might be, it's kind of hard sometimes to tell if an alcohol is there. I look for the carbon oxygen stretch on the primary, secondary, or tertiary alcohols. But another way of doing it is add sulfuric acid and heat your sample, and heat it until it will dehydrate. And then once you've heated with sulfuric, you can go on and add your nitric acid, and then go on and heat with perchloric and bring it up to fumes, and it will take just about anything in solution. Thanks, Autumn.
Great, thank you so much, Paul. All right, so once you have your samples in solution, you're going to want to run those on your ICP. So again, for mercury and nitric matrices alone, you're going to have issues with sticking to plastic, and a lot of instrument components are going to be plastic. And so if you do have access to a glass intro system, we recommend using that for mercury, especially if you're in nitric matrices. So your initial analysis is not really going to be affected by this. You're still probably going to get good results for mercury, but this is going to cause issues for future analyses with memory effects and washout of that mercury. So we recommend running a hydrochloric acid and thiourea rinse solution, and just increasing that hydrochloric acid to get the mercury to get out of your system. So again, one of the issues for mercury is if you do have that dimer and it disproportionates into the mercury 2+ and metallic mercury, you're going to get really high results. So even just a small amount of the metallic species is going to have a really high transport efficiency due to the volatility, and it's going to flood your plasma, and you're going to get really high results, could be up to several 100% recovery. So if you are seeing these really high results, you can generally attribute that to the reduced mercury species. On the other hand, if you're getting low results, your mercury is probably being lost either due to adsorption, or you had that diatomic mercury present in your standards, and you mix with chloride or some other type of ligand where it was reduced and disproportionated into the metallic mercury or precipitated out of solution, so that you had loss of mercury in those standards. So those are just kind of the main things to look for if you are seeing these types of results. And if you can't figure out what may be occurring, definitely just give us a call. We'll be happy to look at your analysis and help you figure out what's going on so that you can get good results. So that's going to bring us to our second polling question. We just wanted to see how many of you all are using ICP-OES or ICP-MS spec, or if you all have access to both. So I'm just going to give you a few seconds to go ahead and answer that. All right. So it looks like a lot of you all have access to both, or primarily mass spec only. So we're going to keep this in mind because our recommendations for rinse solutions for the rest of the presentation, sometimes they're going to be based on your specific type of instrument. So for ICP-OES, this is just kind of a general recommendation, not only for mercury analysis, but just in general. We recommend using RBS-25 as a rinse solution to recondition your spray chamber surfaces. So this is going to prevent the surfaces from becoming sticky and causing issues primarily for those stickier elements, so mercury or bismuth, some other elements. So that's just kind of a general recommendation. And RBS-25 is a commercially available cleaning solution. So this is going to be really good just to use as a general rule of thumb. However, for mass spec, we don't recommend using RBS-25 just due to the high sodium content of that. So that's just going to cause more issues in your instrument. So you don't want to use that there. So the main place you're going to see sticking of mercury, as well as many other elements that are sticking in your system, is going to be the sample lines. And so if you can replace your sample lines, if you're getting a lot of memory effects from mercury, it's probably going to help a lot just to replace those sample lines. And especially PVC tubing, primarily, we've found is especially sticky for these analytes. So for your general rinse solution, we recommend using hydrochloric acid and thiourea. So 1 to 10% hydrochloric and 0.5% thiourea to get that mercury out of your system. And this is also going to be really good if you are stabilizing with gold, because this rinse solution works really well for purging the gold from the instrument as well. There's also a basic rinse type that we recommend, and that's the ammonium hydroxide at 1 to 5%. And that's going to be for both OES or mass spec. So we've just listed out some lines here that you are going to want to look at for mercury. Generally, we recommend looking at the 184 line because it's got good sensitivity and it doesn't have any spectral interferences from other analytes that may be in your analysis. But we do recommend always looking at multiple lines just to make sure that those lines agree and you're getting good results and there's no interferences that you're not accounting for. And for mass spec, we recommend the 202 line. However, there is a tungsten interference here. So if you do have tungsten in your analysis, we recommend using the 201 line. But the 201 line has a rhenium interference. So if you have rhenium in your analysis, the 201 line is probably not going to be the best one to use. And then there's also the 199 and 200 line for mass spec. So again, just make sure you're checking all of those, or as many as you can, just to make sure that you're accounting for any interferences. So that's really all we have for the first half of the presentation for mercury. But I did want to just point out some applications for mercury testing that we expect to be on the horizon. So the cannabis industry has been growing rapidly, and we expect that to continue over the next few years. And some of the elements that are of particular concern for cannabis are the heavy metals. So that would include mercury, and we expect that to have a big impact in our industry. So another recent development is the Baby Food Safety Act of 2021. So this act is going to require, it's going to have consistent limits across all manufacturers for the presence of heavy metals in baby foods. And so this is going to be of particular concern because of the neurotoxic effects of heavy metals. And so that's going to be really concerning for safety and development of babies' brains. So previously, manufacturers were just required to have testing of individual ingredients, but this new development is going to require that the final products be tested as well. And so not only is that going to increase the number of samples being tested, but it's also going to increase the complexity of the matrices and different testing types. So just something to look for in the future for mercury analysis. So that brings us to tin. Tin has lots of testing applications as well, kind of similar as for mercury. Tin is an analyte under USP 232. It's a class 3 impurity, whereas mercury is a class 1. There's also applications in environmental, of course, manufacturing. A lot of cookware coating is made from tin, tin cans. So lots of applications for tin and lots of folks interested in the levels of tin in the samples. So the primary issues that you're going to run into when analyzing tin are volatility, kind of similar as what we saw with mercury, as well as the tendency to hydrolyze out of solution as the tin hydroxide. And so this is going to form a very fine semi-colloidal suspension that's going to be a little bit difficult to see in your standards. And we'll go over that a little bit more later in the presentation. So the forms of tin that are going to be in solution are the tin-4 and tin-2 ions. And both of these are going to form complex ions in solution. So the problem form of tin is going to be your tin-4. And the tin-2 is going to easily be oxidized to tin-4 just by the air. So the age of the samples is going to matter as well, because you're going to have probably a higher amount of tin-4 present in more aged or older samples. So tin can be stabilized in hydrochloric acid alone, but it's going to require a large excess of hydrochloric acid to stabilize the tin. Because again, the tin-2, which is kind of more the form that you want in solution, is going to slowly oxidize to the tin-4. Tin is not going to be stable in nitric acid alone. It will oxidize to form the insoluble stannic oxide. So you're not going to be able to use a nitric acid matrix, unfortunately. So again, the hydrolysis and oxidation are the main concerns for tin. Similarly to what we saw with mercury, you're not going to want to have tin in a basic media because the tin will fall out as the insoluble hydroxide or sulfide. One thing that I do want to point out is that if you're working with tin in environmental water samples, most of that tin is going to be found in the sediments because organic tin compounds adsorb to the sediments at the bottom of streams or lakes or environmental systems. So most of your tin is going to be found in the actual sediments at the bottom of the water. So again, the age of your tin solutions does matter, as the ratio of tin will change over time if you're just stabilizing in hydrochloric acid alone, and if that tin is not fixed in solution somehow. So that's going to bring us to our third polling question. Does your company allow you to use HF in the lab? So I'll give you guys a few minutes to answer that. All right, awesome. So it looks like the majority of you all are able to use HF in the lab. So that's great. HF is really good for stabilizing certain elements in solution. We use HF in our lab, and it's really helpful for certain elements. So we will keep in mind, though, some options if you aren't able to use HF for sample prep and other concerns. So the best option for stabilizing tin in solution is hydrofluoric acid. So the HF will fix the tin in solution by forming fluorostanates, and that's going to eliminate any future issues for oxidation or hydrolyzing your tin out of solution. So that brings us to our sample preparation. So for tin metal, you can dissolve that in either nitric acid and HF or in HCl alone. So we perform both of these reactions in-house for our tin concentrates, and we're able to get tin metal in solution with either one of those methods. But if you are using hydrochloric acid, you're going to want to make sure that you keep a closed vessel and heat that under reflux, because the stannic chloride does have a really low boiling point. It's only about 114 degrees Celsius. So you're going to have loss of tin if you don't keep a closed vessel for that. So I'm going to go ahead and turn it over to Paul just to talk a little bit more about the chemistry of tin in HCl.
When I started working in the reference materials industry, I noticed that tin was available commercially largely as the chloride. And the use and the popularity of tin and nitric acid, wasn't there because of the stability. But as people became more and more familiar with HF, we started producing tin from the get-go in nitric trace HF. You don't need to have an excess of hydrofluoric acid to keep your tin in solution. Now, what we're talking about is trying to get around the problems that Autumn has very nicely described. The volatility of the tin in the +4 state, the tin 4 chloride, if it would just stay as the tin 2 chloride, that's great. When you put it and dissolve it in HCl, that's how it starts. And we've been able to keep tin standards away from the air and keep tin stable for a long, long time. But you have to work in glove boxes. You have to work under conditions that are not convenient. They're not comfortable. The HF is, we think, a simple solution to this problem. And for those of you who can't use HF, check and see if they would be allowed to use fluoroboric acid, because we have produced a very high purity, or not a standard, but a reagent that contains HF that is available through the fluoroboric acid approach. But the chemistry we're dealing with is really, here it is. It's not real complicated, not a lot to remember, but boy, it can sure cause a lot of headaches. Thank you, Autumn.
Thanks, Paul. So another sample type is going to be alloys. So for alloys of tin, we recommend first treating with concentrated sulfuric acid and boiling until that alloy disintegrates and nearly all of that sulfuric acid is expelled. So you do want to make sure that reaction goes to completion there, and you're getting all of that sulfuric acid out of the sample. So after the sulfuric has been expelled, you can either dilute that with concentrated hydrochloric acid or concentrated hydrofluoric acid and just heat that gently to complete the reaction. I do want to point out, though, if you are using hydrofluoric acid, to make sure that you're using a plastic container, as again, that HF is going to be caustic to any type of glass that you may be using. So another sample type is ores. So for ores, we recommend a fusion reaction. And the fusion mixture that we usually like to use is sodium carbonate. Sodium carbonate can be found in pretty clean starting material. It's easy to use, it's safe, and it allows you to use a platinum crucible. So once you've completed your fusion reaction, you can just dissolve with hydrochloric acid and preferably a small amount of HF if you're able. So I've listed a couple other fusion mixtures that will work as well, but I do want to point out, if you're using sodium peroxide, that these reactions can become very dangerous. And so make sure that you're paying special attention to safety measures to make sure that you're safe when you're using any type of peroxide. So I'm just going to let Paul talk a little bit more about using sodium carbonate for fusion mixtures and why we like to use this.
The use of the technique of fusion is you can't survive without it. The nitric acid or the other acid digestion methods are great. We use them predominantly, but there are times when you just absolutely have to do a fusion. And if you look through the literature, you'll see references to the use of sodium peroxide or nitrates, and these are also very, very good methods. However, for the inexperienced analyst, they can be problematic. Too much peroxide with too much organic, or even nitrates with too much organic, heated too quickly can lead to problems. We use and recommend the use of sodium carbonate. It's a very safe mixture, well, actually a very safe reagent. We'll use it by taking the sample, weighing it out, and mixing it in a platinum crucible, which working with platinum is so much easier. The peroxide fusions will generally recommend a silver or a nickel crucible, really is the one you see a lot of reference to, and iron is another crucible material, but platinum is so much cleaner. The carbonate fusion and that doesn't take place until what we'll do is we'll take the sample, heat it up to about 500, 550, and put it in a muffle. If it has to go overnight, you can take even several grams of sample and ash it down. And then the carbonate's mixed in it already before you put it in the muffle. Then just bring your muffle, if you have a programmable muffle, bring it up to 1,000 for 15 minutes and then have it shut off. And you'll be left with usually a fusion mixture. It's very easy to get in solution, just adding dilute hydrochloric acid. In the case of tin, I would recommend that usually about a 6-to-1 molar ratio of fluoride to the metal expected content. You don't need excess in order to stabilize your tin. So the next time you need to do a sample prep and you think, well, I don't really want to do the peroxide or a nitrate fusion, you can give us a call. Think about using sodium carbonate. It can also be obtained very, very, very high purity form. Thank you, Autumn.
Thank you, Paul. So that brings us to organic tin compounds. And so similar to what we saw with organic mercury compounds, organotin compounds are going to be very toxic. So if you are working with these, just make sure that you're taking proper safety precautions again, to make sure that you're keeping yourself and others around you in the lab safe. So one of the main concerns is, again, the volatility of the tetrachloride, as well as the precipitation of stannic oxide. So kind of like what we saw for mercury as well, we don't usually recommend dry ashing, not only because of the loss of tin, but also the stannic chloride or stannic oxide can react with the crucible. And so that's going to cause issues with not only loss of your tin in your current analysis, but also contamination for future analyses that you're doing using that crucible. So that's something that you just want to keep in mind for these type of reactions. So for organics, we usually recommend an oxidation reaction with sulfuric acid and hydrogen peroxide. So you want to heat the sample first with the concentrated sulfuric acid until you get fumes, and then you're going to complete the reaction by adding the hydrogen peroxide dropwise to the solution. So we did underline dropwise here because we want to emphasize that the hydrogen peroxide needs to be added very slowly and with patience to make sure that you're not getting a buildup of that hydrogen peroxide in the sample, which can lead to potentially an explosion. So just be very careful and aware that you need to add the hydrogen peroxide really slowly. So these type of reactions work really well for polyvinyl chloride specifically, if that is your sample type. So the last sample prep we have is the oxide. So stannous oxide is soluble in hydrochloric acid, no issues there. However, as we talked about before, stannic oxide is insoluble. It's very resistant to all acids, even hydrofluoric. So again, for stannic oxides, we recommend fusion with the sodium carbonate, as we talked about before for ores, followed by a dissolution in either hydrochloric alone or preferably hydrochloric and a little bit of hydrofluoric acid. And as Paul spoke about previously, not a lot of HF is needed, just a little bit to keep that tin in solution. So another fusion option is sodium carbonate and sulfur. So equal parts of both of those is going to form the soluble thiostannate in either just water or dilute acid. So that brings us to question number 4. Our polling question: do you have an HF resistant system for your instrument, or is your system glass only? So we'll take a few minutes to get your feedback on that. All right, give you a couple more seconds. All right, so it looks like most of you all do have glass components in your system, more than half. So we're going to keep that in mind for our next slide so that we can give you all some recommendations for analyzing tin on your ICP. So again, tin is going to be best stabilized in hydrofluoric acid, but the HF is going to be caustic to the glass components of your intro system. So one recommendation that we have for folks who only have a glass system is that you can neutralize the HF in the solution with triethanolamine prior to running the samples on your instrument. So you just want to add T to a slight excess of about 7 or 8 pH because that fluoride ion itself is not going to cause issues in your system. You can run those once you've neutralized the HF because only the HF itself is going to cause issues for your glass system. So one thing we do recommend if you are using triethanolamine for neutralization in your system is that you switch out your wash solution prior to any future analyses, particularly mercury analysis. So I'm going to turn it over to Paul to talk a little bit more about why you want to switch out the wash solution.
We found out quite by surprise that the presence of triethylamine in your wash bucket will reduce mercury to the metallic form, and the mercury vapors actually make it up through the wash disposal area, the waste, up into the plasma, and you'll get really huge signals for mercury that way. I do not want to discourage the use of triethylamine, though, because it's a wonderful agent for stabilizing a lot of your metals that are fluorinated, and things not just with tin, but hafnium, zirconium, titanium. There are a number of silicon, a number of your fluorides that are stabilized by T, and it allows you to use all glass systems. That's really the key message that I had on this. What we would do at that time was we would just use, if we were doing mercury, we would have a separate wash system for it, because the presence of the T doesn't affect anything else, just the mercury. Thank you, Autumn.
Thank you, Paul. So once you have your tin in solution, you're going to want to run on your ICP. So some issues that you're going to see if you have tin stabilized in hydrochloric acid is, again, those issues with the polyatomic interferences for arsenic and selenium. So again, if you just use the collision cell or helium mode for your ICP-MS, that's going to eliminate those issues. Another issue is, again, for the tetrachloride, which has that low boiling point. So it's going to have a high vapor pressure and high transport efficiency to the plasma. So you're going to get high signals if you do have that tetrachloride in your solution. Another concern is if there are different ratios of tin-2 and tin-4 in your standards that are stabilized in HCl, you're going to not get very good results, because if you have higher amount of tin-4 in your standards in your samples, you're going to get low results for your samples because more tin is going to be getting to the plasma from analyzing your standards. So you're going to see a lower result if you have less tin-4 and more tin-2. So the best option to eliminate this, again, is to fix with a small amount of HF to make sure that you're not seeing those issues in the instrument. Another issue is if your tin has undergone hydrolysis, you will have that semicolloidal suspension of the tin hydroxide in solution. So again, before you run your samples or your standards, you want to make sure that they are crystal clear. Again, the suspension is going to be very fine, so it may be difficult to see, but just make sure you're taking a look at those before you run the analysis. So I'm going to turn it over to Paul to talk a little bit more about issues with this and how you can solve issues and what you may see if you do have the suspension present in the solution.
Tin is probably your best opportunity to get what I've been calling a semi-colloidal suspension. Tin hydrolyzes, the tin plus 4 has the highest hydrolysis constant. It hydrolyzes more easily than any other element or oxidation state in the periodic table. Tin-2 is bad, but nowhere near as bad as tin plus 4. When you're adding, now, so remember that if you decide that you have to stabilize with a little HF, always add your HF when the solution's still acidic, because it's the HF that will react with the tin in much the same way that it reacts with fluoride and other elements. It needs that molecule to come in and react with the metal, not the free anion. the free fluoride ion is pretty harmless, pretty non-reactive, at least in this particular case. So then you can actually take the tin and you can go on then and neutralize a solution and bring it to a pH of 7 or 8. It will remain in solution. You can have your HF, you can have your fluoride stabilization, of the tin. You won't have HF at that point. You'll break the HF molecule. Its hydrolysis, its pKa is 4 roughly. So it's a weak acid. It'll react with the triethylamine, or the T we call it. But the good news is you've got your tin stabilized. Now, let's say that you look at the solution, everything looks hunky-dory. We know that this chemistry is dependent upon order of additions, how much is there. It gets really, really, really complicated when you start mixing solutions, and you have literally to the nth power possible combinations of reagents and elements. What I want to encourage you to do is always suspect that you might have, at least in your validation phase of your method, that you might have a semicolloidal suspension, because you'll look at the solution, it'll look clear. You won't see any precipitate. Run it through your plasma, then take that same solution, filter it through a 0.2 or 0.3 micron millipore, and then run it again. Usually, if there is a semicolloidal suspension, what happens is your signal will go up. You think, oh, Paul, we're gonna filter it out. You don't. The semicolloidals, they'll break apart. And what you need to get into your nebulization system is something that's just a small. Here, Autumn has 8 microns or less. So these large particles are not going to make it in, but they get broken up, and then you start getting the smaller particles in. So you're almost taking an approach, something like a slurry nebulization approach that Dr. Les Ebden has written so much about in his research. So Autumn, thank you for that.
Thank you, Paul. So that's going to bring us to our rinse solutions and what you're going to want to use to get the tin out of your system. So sticking for tin is more of a concern for mass spec than OES. We don't really have issues with tin sticking in the OES here at IV, but we do recommend a pretty high hydrochloric acid wash for your rinse solution. So 10 to 20% hydrochloric acid, if possible, is going to help get that tin out of your system. So adding HF is also going to help get tin out of the system. It's kind of been the theme, but the HF is definitely going to help. If you have OES, you're going to want to keep that to between 0.1 and 2%. For mass spec, it's going to be lower concentrations. And then we don't recommend anything over 0.2% if you have borosilicate components, as that is going to cause issues with disintegrating your glass components, and you're going to have issues with boron and silicon results. So just to keep that in mind if you do use HF in your rinse solutions. So if you do have an HF resistant system, we still don't recommend going over about 3% HF, because anything over 3% is going to start to degrade that coating. So you want to be really careful about that, even though it is technically HF resistant. Higher amounts of HF can still cause issues. So if you're still seeing tin in the system, we recommend, again, replacing that sample tubing first, because this is probably going to be the area where you're having the most issues, and this might eliminate your issue altogether. But if not, it's going to greatly reduce the amount of tin that you're seeing in washout. So just some things to keep in mind there. So we've listed some of the lines to use for tin analysis for OES and mass spec. Again, we recommend looking at multiple lines if you can, just to make sure that you're getting consistent results. So for tin on OES, we usually recommend the 189 line. There is a gadolinium interference here, but you do have good sensitivity, and it's probably going to be your best line as far as interferences, because the 242 line as you can see here, has a lot of interferences. So if any of those elements are in your analysis, you're going to want to keep that in mind if you are looking at the 242 line. Just kind of an interesting thing to note, the 189.989 and the 189.926 lines are actually the same line for tin. It just depends on the type of grading in your particular instrument. So just something to keep in mind. Those aren't actually different lines for tin. It just depends on your instrument. But again, that line is going to be the best for sensitivity and interferences. For mass spec, we recommend the 120 line, although there is an interference from tellurium here, and to a lesser concern, ruthenium and palladium interferences. And so if you do have any of those analytes in your analysis, make sure to check the other lines as well. So the 117, 118, and 119 lines are also good for mass spec, and you should see good agreement across all of these lines on mass spec. So that will conclude our 10 portion, and we'd like to go ahead and take the next few minutes for any questions.
All right, thank you, Autumn and Paul. We'll now move on to our question and answer portion of the session. I'm going to read the questions from our attendees, and hopefully we'll be able to fully answer them all. If not, we will definitely reach out to you by email to follow up. Also, if you think of a question later after the conclusion of the session, feel free to email us at info@inorganicventures.com. And also, rest assured, a copy of the slides of this presentation will be available for download on our website early next week, so you can look up some of those wonderful references that were sprinkled throughout the talk. So now for our first question. How does your EDTA and mass spec methods compare with cold vapor AA techniques?
Paul, did you want to take that one?
The cold vapor approach is a technique for mercury that we haven't used. Usually the cold vapor is you add a reducing agent, you form the metal vapor, gases are swept through and the mercury is swept through a quartz cell. And a lot of times, at least it started out being atomic absorption measurement. We use plasma emission, EDTA, and then looking at the metal itself. So we're looking to get all three of those methods agreeing with one another. But I have not, to my knowledge, and we have a lot of customers that use mercury and do cold vapor. In fact, that's the primary method still, and I think one of the best, if not the best. Mm-hmm. But we do not use that here.
All right. Our next question. What would be the effect of using straight gold versus gold trichloride for stabilizing mercury?
When we saw, I'm sorry.
So gold in solution is going to, so if you have gold in solution, it's going to contain chloride, because you just can't have gold in solution without the chloride. So as far as it's going to be gold chloride in solution. So I hope that answers your question.
If I could add just a little bit on that.
Sure, yeah.
I was real curious when the EPA came out with, I think, this very excellent approach for stabilizing mercury. By the way, I applaud them every time I look at the reference. It works very, very well, and we've seen published people say, "Well, the gold acts as a strong oxidizing agent." I think it also may form a di or even a triatomic molecule with the elemental mercury. But this is a good question. I don't know how the metallic, if the mercury, my guess is metallic mercury would probably played out on the gold because it wants to amalgamate with it. Gold amalgamates with platinum, mercury amalgamates with platinum and with gold very, very readily, very easily. And I don't know that it would help as a stabilizing agent. It would probably just remove the metallic mercury from the solution. If you put, let's say, gold metal in a beaker container with mercury, with elemental mercury, or the mercury atom, which the mercury zero valent atom suspended in solution.
Right. I did want to point out, we do have a gold and nitric standard here. So our CGAUN1, that was actually referenced in the gold trichloride slide. And so the matrix for that standard is nitric acid, but the starting material is a gold chloride. And so there is still chloride in that standard. And that's one of the standards we recommend using actually for this, for stabilizing mercury in solution, as that's also, that standard is not going to be stable, just FYI, when you mix it in solution if you don't have a hydrochloric acid matrix, or at least hydrochloric acid in the matrix.
All right. Our next question, what acid concentration is recommended to stabilize mercury in solution? And I would point out what would it be for nitric and or HCl?
Bipolar nitric.
So for HCl,
that's not right. 5%. I apologize.
Oh no, you're fine. We usually stabilize in just kind of our standard matrix is 10% hydrochloric acid. But depending on what your needs are, you can probably go lower than that. Any amount of hydrochloric acid is going to stabilize the mercury, as far as what we found for our standards. And then for nitric, we recommend 5 to 10% nitric for stabilization of that. But again, if you have low level mercury, you're going to need to have either a glass container or the gold to stabilize that in the plastic. So just some things to keep in mind.
I would add to that too, Autumn, with I've noticed on our mass spec, you can go as low as 1% HCl for lower levels of mercury, and I don't think we've seen any stability issues. If we go to nitric, though, we have a lot of problems. Even with gold from time to time, it doesn't last forever, so just keep that in mind, run it versus fresh standards, and make sure you're testing what you think you are. All right, we have a couple more questions. We're going to pivot over to tin now. What concentration of tea is recommended?
So we recommend just neutralizing on a 1-to-1 molar basis. So it's going to depend on the concentration of HF in your standard. So if you don't know the concentration of the HF, I would just recommend neutralizing and checking the pH to make sure that you have neutralized all of the HF. But we do recommend neutralizing on a 1-to-1 molar basis of T to HF.
All right, and kind of a follow-up question. Is there a preferred brand of tea that you would recommend?
I don't have a recommendation for a preferred brand. Paul, did you have any?
Yeah, tea is manufactured from propylene oxide and ammonia. Excuse me, it's ethylene oxide and ammonia. Pardon me. It was first made, I think, by Union Carbide. That particular molecule is made by a number of people, and they distinguish whether it's technical grade or not by how much di and monoethylamine is in the mixture with the triethylamine. When I've worked with it for a long, long time. I've always wanted to to buy more of the technical grade of material, because what I would check for would be trace metallic impurities. You don't get any cleaner or dirtier with the grade of tea if you use a technical grade. you get a little greater variety of molecules in with the triethylamine, and I like that because I intentionally mix in things like di and monoethanolamine anyway in certain applications, along with a T-tetraethylene tetramine, and I'll throw in some EDTA and use all of this concoction to stabilize pretty much the periodic table at a pH neutral or slightly basic condition. I don't know if I hope that answered the question. Did that make sense?
I think so, and I'd like to add to that. Paul mentioned that we've done trace metals. We care a little bit more about the trace metals that you find. So, not necessarily the brand of tea that you get, as Paul said. No matter what kind of tea you get, it's going to have only impurities of diethanol or ethanolamine. Metallic wise, what is the triethanolamine packaged in? So I would say worry less about the brand that you get and maybe more of how it is shipped to you. Is it stored in glass or is it stored in plastic? You'll find that the trace metallic impurity profile is going to be a little bit different. All right. Only a couple more questions have come in. What is your opinion of using the Tin 118 line?
Paul, did you have any experience with the 118 line?
I'm looking at my
from
guide.
a mass spec lines table.
I think 118 usually works just fine. It's got 24% abundance. It's only a little bit lower than the 120. I would trust the 118 a little bit more because the only things around it are other tin isotopes. The 120, like Autumn pointed out, has a tellurium interference, so that's an isobaric one. So if you have any tellurium, 120 is not going to be usable. But yeah, 117, 118, and 119 should match each other most of the time.
Mhm. All right. Thanks, Thomas.
No problem.
Thanks,
And I
Tom.
think this is. Oh, we got a couple more. All right, so I have another 10 question. So I ran 10 samples with both ICP mass spec and ICP-OES. I found that 10 results from the mass spec are higher than ICP-OES. Could you give me some suggestions on what could be the issues?
The mass spec was higher than the OES. Well, a couple of things come to mind. First, on your OES, I'm not saying you didn't do this, but check your emission spectrum of the line or lines that you're using. Make sure there's not a background interference. It doesn't have to be direct spectral overlap, but a background interference will cause your result to come out lower. One way to confirm that too would be to try a couple of different 10 lines on your OAS to see if they are agreeing with one another. If you can get 2 or more 10 lines to agree, then you've very close to, if not proven, that there isn't a spectral issue with the optical emission result. In terms of the stability of the standard, et cetera, on the mass spec at low levels, just make sure your matrix is dilute nitric, 1% on the mass spec, let's say. And I'm going to ask you guys here, the IV people, do you mostly run in 1%, don't you?
Mm-hmm. 1%.
Okay.
Yeah, 1% HCl.
Yeah. Okay. You run that way. The mass spec, the other thing would be the same thing, is try a couple of different masses to see if you get agreement there. Because first of all, we want to find out if you've got an isobaric. You want to find out if there's an interference or if there's a viscosity, surface tension, matrix effect going on. If the differences are slight, it could be matrix. But if they're gross, big effects, is usually spectral.
Yeah, there are a couple ways that the mass spec signal could come up high. I'm looking at the isotope chart, and I mean, if your sample is coming out high, perhaps you have maybe even something like uranium in your sample also that could be giving you a doubly charged interference on the tin mass you're looking at. So, I mean, I would recommend looking at every tin line and making sure they agree, because they should.
Mhm.
All right.
I've always found that looking at the spectra, both on the mass and the emission, optical emission end, looking at those actual spectrum that the software is trying to take and take measurements of intensity, I found that to be absolutely priceless, necessary in order to give me some idea as to what might be going on.
Mhm.
All right. I think we're going to flip back to Mercury for this next question. Is everything you said about HCl valid for aqua regia as well?
Yeah, so mercury is going to be stable in aqua regia as well, as long as you have that hydrochloric acid in there. That is going to stabilize your mercury. So you can have nitric, it just needs the mercury to stabilize in plastic containers. So.
All right. And I think this is our last question that we have at the moment. Some of my samples I need to use nitric and HCl to digest. Can tin stable in the matrix of nitric and HCl? I guess, is it stable in the mixture? So typically the final concentration of the test solutions is 15% nitric and 15% HCl. Ooh, that's pretty high.
I would think so. Wouldn't you, Autumn?
Yeah, I was gonna say it depends on your how high your hydrochloric acid matrix is, but it sounds like you have a pretty high matrix, so that should stabilize the tin that you have in there. And again, it depends on the tin concentration as well, but I'm sure you're running low enough levels that 15% is going to be plenty for stabilization.
And that's yeah, that should be good.
Mm-hmm.
All right. Well, that's all the questions we have for now. So thank you, Paul and Autumn, for sharing some thoughts on tin and mercury. And thank you, everyone else still watching, for taking some time out of your busy day to join us, and also sticking around through the Q&A portion. We only went over by about 20 minutes. I think we did pretty good today. We hope to see you again for our next webinar that is scheduled for Thursday, July 1 at the same time. Mike Booth and I will be presenting superior custom blend analysis by radial axial ICP-OES, a robust calibration method that reduces interferences for 69 elements. So thank you and enjoy the rest of your day.
And thank you, Thomas.
Thank you.